Okay, I think we start. We don't have a waiting room setting, so if people are joining later, this will be a smooth transition without interruption. I want to welcome everyone. My name is Mona El Kafif. I'm an associate professor here at UVA School of Architecture, and I want to welcome everyone to our today's lunch lecture, Biophilic Material Research. Maybe to give everyone a little bit of an overview how this lecture series emerged. We have currently an exhibition in our halls entitled Biophilic Region, Charlottesville-Albemarle County, a vision for a nature connected future. This exhibition is up this month. So if you are around in Charlottesville or in Albemarle County or in Virginia, please come and visit our school. The exhibition is featuring a series of projects and was originally initiated to work that was developed in my seminar where we looked at the potential to foster a combined application for the city of Charlottesville and the Albemarle County to apply for the Biophilic Cities Network. And with their collaboration, we could launch a new model, which is the idea of a biophilic region. Just to give you a little bit of an overview about the work that is featured here, we have though it's a small space, quite a bit of material exhibited, stretching from the asset analysis of the biophilic region that, as I mentioned, I conducted last year with my students in my urban strategies class, as well as work that comes from our colleagues in urban environmental planning and in architecture and beyond. I just have a couple of images to show you what you could discover while you're in our exhibition. This is just an overview of the work of the asset analysis and the design that would emerge from there. We also have media terminals that feature the work of our colleagues in planning, the Biophilic Cities Network, Beth Wilson, Barbara Brown-Wilson, and Karen Firehawk on green infrastructure. We also have the beautiful work featured by Lara Gastinger, who is a real expert in drawing plants that you can see here on the back wall. We have the work by Katie McDonald and Kyle Schumann, and hopefully learn a little bit more about their work today, as well as Ehsan Bahalu, who has developed a new prototype entitled The Living Column for the exhibition. We also have media projections of work that was developed in our studios, specifically in the Landscape Foundation studios, taught by Lina Shaw and Matthew Seibert, as well as in one of our research studios, a collaboration between UVA and our parks department in the county, where John Komatsi developed design build prototypes for one of our new parks, as well as beautiful postcards and visuals that feature the biophilic capacity of our region, sponsored by Woody Wingfield and the Botanical Garden of Piedmont. And maybe one of the highlights from last week's opening is that the city actually did already apply and received the Biophilic Cities certificate and is now a part of the member network. And me carrying maybe two hats, being a professor, but also a member of the Natural Heritage Committee in the county, we are currently working hard on making this also possible for the county. These are just a couple of images from the event, and there are many students, faculty, and designers who contributed to the work that is currently featured at the school. All of this hopefully to foster new design strategies to address sustainability and biophilic objectives in this context. I want to thank everyone, specifically the School of Architecture's team of communication, our Fab Lab, as well as our tech support, and the Jefferson Trust, who provided the funding for the exhibition. And with this, I want to hand it over to introducing the session today. When we think about biophilic assets, we very often think about urban strategies like tree-lined boulevards, green infrastructure, planted roofs, and vertical gardens that allow us and our cities to be shared between humans and non-humans. These are biophilic building blocks and patterns that shape many visions of a greener urban future. But what happens if we move beyond the idea of the green? Emerging design research expands biophilia in this context into the realm of living and responsive material structures that grow, surfaces that host microbiological communities, and matter that actively participate in ecological cycles. From experimental building systems cultivated with fungi through 3D printed components made of compostable material to furniture and architectural elements designed to be alive, these material innovations challenge our assumptions about permanence, decay, and the boundaries between human and non-human agency. Today, I want to welcome our guest speakers, Katie McDonald and Kyle Schumann of the Before Building Lab, as well as Ehsan Bahalo. I'm quickly introducing all our speakers and then we move on with the individual presentations. Katie McDonald is a licensed architect in Virginia and an assistant professor of architecture at UVA. She's also the director of the material research at the Before Building Laboratory, where she pioneers new biomaterial construction systems. Katie was named Educator of the Year in the Metropolis magazine's Planet Positive Awards in 2023. She works together with Kyle Schumann, who is also an assistant professor of architecture at UVA and the director of the robotics construction at the Before Building Laboratory, where he invents ground-up technologies to make it easier to work with natural materials. Schumann was also awarded the Timber Education Prize in 2024 and the Design Build Award from the Association of Collegiate Schools of Architecture in 2023. Together, they founded an award-winning practice, After Architecture, and the Before Building Laboratory, which advances sustainable construction using renewable carbon sequestering materials with a focus on wood. The lab promotes adoption of sustainable construction techniques by translating research to industry through publishing, patenting, and demonstration projects. And we also have today Dr. Ehsan Bahalo, who is an assistant professor of architecture and the director of computational tectonics labs at the School of Architecture here at UVA. His work is centered on ecological construction to address climate change. His work is centered on ecological constructions to address climate change challenges through research on sustainable materials and robotic construction. He explores novel design strategies to shift the design approach from material and fabrication-centered processes to multi-species design. Dr. Bahalo research projects focus on utilizing bioprinting to create living architecture and upcycling plastics. He explores using mycelium to engineer living materials for biomanufacturing, embedding greenery within 3D printed soil, and upcycling plastics in construction. His research is currently being exhibited in the French Pavilion at the Venice Biennale. And with this, I want to welcome everyone, our speakers and our guests, and I'm handing it over to Ehsan.
Thanks, Mo, for introduction, and thank you all for joining today for our conversation. Let me try to. So, the title of the topic I selected is eco-resilient tectonics. That the object that is presented at the exhibition is one of the series of the object that I am developing under this title. The aim of that is a focus on integrating material capacity and fabrication limitation into design process to develop a novel tectonic system. Uh, the relationship between material construction and the environment is a crucial factor in climate change. Research indicates that the carbon dioxide emission from the built environment exceed 50%. Specifically, 28 of these emissions are attributed to building operations, while nearly 23% result from the production of building materials such as concrete, steel, aluminum, and other types of materials. One approach to addressing these challenges is applying methods such as cradle to cradle or circular economy in building construction. A circular economy presents an alternative to the conventional linear construction methods, which focuses on take, make, and dispose. In the 3R approach, reduce, reuse, recycle, we have the opportunity to minimize the use of material and thus reduce carbon emission. This method aims to repurpose recycled materials and reduce the use of raw material and residual waste. One approach is to develop a multi-species approach to be a part of circular construction. As a multi-species approach, an ecologically driven design emphasizes the resilience of the built environment in mitigating the negative effect of the current building paradigm. It advocates for a holistic approach that integrates ecological solutions into building systems, moving away from anthropocentric designs. This approach aims to improve interaction between human and non-humans in urban environment, reduce urban heat islands, and enhance the resilience of the built environment. Additionally, it includes integrating living organisms into building systems with methods like green facade, living wall systems, and natural insulation materials. The series of examples that I'm going to show you is a transition and our research to develop a building system that can potentially be adopted to the building system. So the first project is ecological active structures that utilize robotic 3D printing of earthen structures to harness local resources and employ digital fabrication techniques to craft intricate geometries. This approach facilitates the integration of living organisms into the printed system, creating ecologically active system or structures. An ecologically active structure is designed to maintain specifically conditions for flora and fauna, ensuring ecological performance of earthen structures without the need of chemical additives. In this process, seeds are integrated between the 3D printed layers during additive manufacturing. Generally, stabilizers like cement and lime are traditionally used to enhance mechanical properties of an earthen structure. However, the challenge in this process lies in preserving the soil chemical structures while still supporting seed germination for growth. This example shows our collaboration with the material scientists and environmental scientists who we work together to test different kind of mixed design for earth construction. And in that example that we try to test different type of geometry to see if our recipe can accept different kind of overhanging and also can have a germination on top of that. Ecology active structure represent an innovative combination of material and fabrication method designed to create living building system utilizing limited local resources and a biotic system. From those small objects, I gradually started to transit to the a little bit larger scale that can be applied for the building system. This moving toward living building system, this system provides a scaffold for growing biotic system. Biotic means a living organism or living component, or in this case, a greenery. Or a simple example is subsequent wall section that facilitate the germination and growth of plants between and on 3D printed layers. This is the time lapse of the project that we developed. It shows the germination happened and the root started to move on the surface between the layer after 48 hours and into 96 hours. Then you can see the germination and around 150 hours, then you can see completely just grow. This project we already put it under observation about 2 to 3 weeks to see how they just move from the germination to seedling and how it can just be adjusted to the other green facade system. In addition to the green system that I work, I also are interested to use other species, other organisms such as mycelium. Mycelium composite derived from the vegetative part of fungi serve as natural binders for agricultural waste, creating sustainable insulation materials. These composites provide both thermal and acoustic insulation and can be used to remediate soil-based structures. Additionally, mycelium composite possess self-healing and regenerative properties, making them ideal for engineered living materials. So the whole idea was when we just have this kind of uh, uh, green wall system as ecology active system, it was a whole environment between those that that I thought that it would be possible to just add insulation material to do between those. To have an insulation, then I just moved toward the mycelium composite system that has been proved that can be used as insulation material. So this whole series is just try to see how we can just integrate mycelium in the earth structure. Eco-resilient tectonics, eco-resilient tectonic structure aim to develop living materials that maintain active ecology, enabling self-regeneration in adverse conditions. This research focuses on creating multi-species structures. Specifically, this research using living organisms leveraging innovative fabrication systems to advance living materials. So this is a macroscopic image of the interaction of the soil and mycelium to see how they can entangle with each other and how they behave. And the whole idea was the goal is to develop a 3D printed wall system that incorporates natural insulation from mycelium and include greenery. Experiments tested the feasibility of integrating these living systems within the structure, showcasing the self-healing capacity of the mycelium composite. The development of an eco-resilient tectonic structure involved a robotic earth 3D printing system, mycelium spawn preparation, and green active structure preparation, and the mycelium living system and mycelium living structure preparation. So in that case, what we have done, preparation of the material, biological process of that, and then 3D printing, integrating mycelium and seed, and then I try to see the degradation of the whole system and how it will happen. The preparation of the green active structure involved investigating the growth behavior of microgreens on 3D printed earth blocks. Experiments conducted with curly cress, reddish, and white clover provide a valuable insight into root growth and behaviors. So I tested different kind of microgreens and to see how they just behave between the layers, how the root of that work on the surface. And from that one, I just selected a reddish for the final prototype due to its excessive root exploration and successful germination on the block. The block were maintained under controlled conditions with high humidity and room temperature, which supported seed germination. In parallel, I just work also to see how this mycelium can be integrated to the 3D printed earthen block. Preparation of the mycelium spawn involve series of processes. It's good to know that we just have a sterilization, a mixture of soil, hull, and oak pellets, injecting liquid culture and incubating under controlled condition. For this example, we tested different kinds of mycelium strains from reishi to blue oyster mushroom. And blue oyster mushroom is a fast-growing fungus species, help reduce incubation time. Experiments explored growing mycelium spawns in 3D printed earth blocks, indicating the feasibility of growth with consideration to avoid contamination. So the preliminary test conducted by reishi, which is provided by EcoWative, And then we noticed that during our observation, we noticed that the mycelium can penetrate and pass through the 3D printed layers. That was very promising for us to move forward. And after that, what I've done was putting all of them together and see how they behave. This is the left side shows the you can see the germination of the clover and casting of the mycelium spawn. And then in the right, after 1 week, you are going to see the germination stands. And then also we have a mycelium started to completely become white, and the colonization is very successful. This preliminary test provided enough evidence that I can apply it in some kind of wall structure that for the final wall prototype, this is the prototype that we work. We designed a self-standing structure with dimension of 150 millimeter, which is about in width, and 30 centimeter in length and 90 centimeter in height. With addition of those bars or bars, it goes about 120 centimeter. To ensure the mycelium receive adequate oxygen, so we just define some channels that air pass through to reach to the bottom of the prototype. Taylor, thank you. So to reach to the bottom of the composite, and these reinforcement bars also were considered to improve the structural integrity of the mycelium composite and the integration with the 3D printed wall. Additionally, we experimented with a reddish instead of white clover for the exterior wall. So the results successfully demonstrated an integrated living building system with microgreens fully germinated and mycelium composite fully incubated and colonized, creating a new type of tectonics. We can see here the reddish in the left side, and then the exploration of the hyphae on the surface over here. I don't know the top of the prototype. And here also is a back of the prototype and how we can control the way that we wanted to have a greenery on our system. During the preparation, because I was very excited to see how it works, it was I opened the cast early, and the result was damaging the whole prototype. You probably can see in the left, we can have the we can see the rebars over there, and also with the mycelium completely cracked. So the idea was, we knew that the mycelium can grow, can regenerate and self-heal itself. Then by putting back and packing the whole mycelium, I gave them about 1 week, and after 1 week, the colonization happened, and it just sealed all the cracks and fixed the problem that occurred during the fabrication process. So this structure remained intact without any sign of cracking, buckling, or deformation, because during this time, it was about 2 to 4 weeks, the whole structure should be in a plastic state, which means that it is not solid. The soil is not dried, because it's required to provide enough moisture or humidity for the mycelium that they can grow, and also it has to provide enough moisture and humidity for the radish to continue to the growth. This research emphasizes the potential of 3D printed earth structure integrated with microgreens and mycelium composite. The finding confirms the viability of creating eco-resilient architecture through the 3D printing of the earth structures. So after this, let me show you the recent publication that is that was the research that conducted before preparing the artifact for the exhibition. This is the microscopic or SEM imagery of the mycelium network that we just need to understand how this hyphae and the mycelium works. This is a part of the a recent publication from the Material and Design journal paper that invests how we are going to develop a nutrient system for the soil, and how that nutrient system with the soil can be printed and can potentially be host the mycelium. In the right side, you can see different kind of nutrition that we tested on the on a petri dish level with the soil, and how this nutrition improve the growth of the mycelium. On the bottom, you are going to see two different sections of that. One is the above the printing, and another one is the bottom of that. That is addressing the main target or aim of this research, to understand three different growth behavior of the mycelium: aerial growth, surface growth, and penetrative growth. In this research, our aim was to target the penetrative growth, to have the most balanced growth between the aerial, surface, and penetrative. This area over there shows every conversation that I done. When it was successful, in addition to that, I wanted to just also test. Let me remove the annotation. In addition, I wanted to test if we can play with this balance of the growth of the mycelium, penetrative, surface, and aerial, to support this, the crack. We just intentionally add these cracks on the three samples, and then it was the mycelium growth on that one. And after a few weeks, it just started to self-regenerate, fill the gap between the soil, and also bridge between the crack that is developed. The whole result is also published, is available online. You can read how I really just developed this research. In addition to that one, this idea that how we can just manipulate the growth of the mycelium was embedded to the artifact. In the artifact, we just started to print a clay with the regular clay with added pigment, and it's not soil anymore. And you probably can see inside of that with a robotically 3D print of that, and inside of that was hollow. And then we cast inside that. After 2 weeks, I might be 2 weeks, we just remove it. You can probably see I just wrap it with plastic, and then I noticed that okay, the mycelium, the growth that I mentioned and coordinated and engineered, passed through the layers that we just add the gap, because I just wanted to add some kind of oxygen pass through, and then the mycelium can just started to grow between those layers. And also we just with the engineering way, we just add nutrition to just expedite the growth of the mycelium on this specific area. And this is the whole artifact that is about 90 centimeter. It is 30 centimeter of that is the core of the mycelium without any support of the clay, and the bottom of that is 3D printed the clay. And this is the image of that. It's just we put it in the exhibition. It is almost after 4 weeks, and then the mycelium growing, different behavior of that, and also started to develop even just fruiting. If you are in a school, you can go and see they just to give the mushroom. And then the top part of that, it just started to provide another layer on top of that to support itself. And this is the whole artifact in the exhibition. For this project and other, I would like to thank my research assistant, specifically my PhD students, Ipsilodata and Yema, for their help on this intense work that we've done to reach to the exhibition. Additionally, because it was a conversation about the biophilic and how we are going to have a conversation with the community, I just put the work of the ecological active structure that is in the French pavilion right now in the Venice Biennale, that showcase how the community and can see and understand the as a part of the French pavilion. This is the combined intelligent section that showcase about this advancement and how we are going to combine our intelligence to have a better and sustainable environment through the technology or through the conventional work of the conservation. Thank you for your attention.
Thank you, Ihsan. Wonderful, really impressive work. I would suggest maybe that we have questions at the end. Also, I have a couple of questions for all of you. And if there are questions that are currently emerging in the audience, maybe put them into the chat and we can pick up after we were able to listen to Katie and Kyle. With this, I want to hand it over to Katie and Kyle, and then we will have hopefully a discussion at the end.
Great. Thanks so much. Can you see our slides okay?
Yes.
Okay, great. Well, thanks so much for inviting us to be part of the exhibition and panel, Mona. It's really an incredible body of work, and excited to follow up Ihsan's beautiful work. Each of those layered assemblies are just super exciting. So I'm Katie McDonald, and this is Kyle Schumann. We develop work through two platforms. One is our professional practice after architecture, and the other is our academic research lab, the Before Building Laboratory at UVA. And foreground material investigations, which bridge conventional construction and digital tools to advance sustainable construction. Today, we'll be focusing on the work of our research lab. And in sharing that work, we want to acknowledge the kind of wonderful contributions of our research assistants. With our lab, our work really expands from a team of two to a team of many, and our goals are to advance circular construction practices by pioneering new material assemblies as well as tools. So getting into our work, we wanted to start with a statement from Mario Carpo that the only way to deal with the inherent capriciousness of living materials is to react to their whims and volitions on the spot and on the fly. And that's a kind of statement that informs our work and really our approach to working with natural materials as a kind of model of co-authorship or collaboration. We'll start with one project that's exhibited in the show, in which we pose a kind of provocation. Can we move from purpose building to purpose growing? And in this project, which is a series of chairs called the parklet chairs, seeds are manipulated during fabrication to shape the growth of gravitropic roots and heliotropic sprouts. So you see an image here of a 3D printed mold with the roots growing together, and the roots are grown hydroponically without soil. And manipulated during the growth phase in order to control the kind of direction of the blades of barley that you see here. The chair seat is made with nothing but barley, no adhesives. The form interlocks with and sits on wooden legs below in this version. And in its final form, the parklet chair we see as a kind of island landscape displaced from soil, water, and sun and resituated into the interior. It also has the kind of added benefit of adapting to the posterior of whoever sits on it. And so for the exhibition this fall, we made a new version of the chair playing with the direction of the barley growth. And so in this case, the barley becomes more like the fringe of a cushion, directed downwards, and then the kind of knitting of roots becomes the seat, which interfaces with the body. And so that's something you can see on view, along with Ehsan's beautiful living column in the exhibition.
So we're gonna pivot now and look specifically at a body of work that's growing, working specifically with wood. Wood is a carbon sequestering, renewable, and well-codified material. And one of the reasons we're kind of focusing on wood now is that it has this long history in construction and offers familiarity. But we also find that wood has been used in pretty consistent ways throughout history, and new technologies are offering new potentials now moving forward. So we'll start by sharing this late 18th century engraving of a sawmill. It's an image that's become pretty important to us in how we think about this material production. And we find this image to be delightfully absurd. It's from an account during the American Revolution by a British officer who was traveling on foot from Montreal to Virginia. The sawmill that's depicted in the image is located in upstate New York, and it rests in the shadow of wispy trees that appear taller than the buildings and taller than the clouds in the background. We see a solitary figure standing within the sawmill structure, which appears to be vomiting or spewing this massive amount of milled lumber into the still water of a creek below. And this industrially processed material disappears under the surface of that water and then miraculously emerges perfectly stacked in orthogonal piles on the left. And this entire process is observed by both soldiers and onlookers who casually lounge in classical repose. Questionably, we find logs are nearly absent from the image. Besides one or two linear elements seen on the hillside, we see only standing trees and then the resultant processed lumber. And so we find in this image that the transformation of this natural bounty of America, of the forests, is turned into mass-produced goods in the form of standardized lumber. And this whole process is represented kind of simultaneously as being immense, effortless, and picturesque. So if we fast forward now around 250 years to today, we'll find the production of lumber more or less unchanged. Since industrialization, humans have transformed the raw arcing forms of trunks and branches, which balance their search for light, water, and structural integrity, into simple orthogonal prisms. Breaking wood down and reassembling it into a uniform and predictable element results in substantial waste and requires a lot of energy and time in the production of what we kind of see still as essentially a raw building material. So through this process, the intelligence of the grown material is lost, and we trade greater embodied energy and waste for ease of construction and faster construction on site. There's perhaps no building product quite so easy and cheap as the humble 2x4, which we're all familiar with, which is optimized not for material economy or intelligence, but for human labor. And this expands to relate to all these dimensional standards in kind of standard building construction. We find then that these standardization practices and material processing efforts were embraced by modern architects. In these images, we see an exhibition from 1931 called The Dwelling of Our Time, put together by Lily Reich and Mies van der Rohe, which displayed full-scale prototypes of modern homes that were surrounded by displays of the materials and products from which the houses were made. And so this was an overt association between industrial materials and modern design that was neatly packaged for a public-facing audience. Closer to today, as new movements in architecture have embraced bespoke form through digital modeling and fabrication, we find that prisms and sheets still often remain the basic unit from which geometry emerges. And so we have, in these cases, the grown intelligence of the tree simplified down to kind of standardized sheets that are then cut through subtractive means and re-aggregated into kind of very customized forms. More recently, timber products have thickened and multiplied from the familiar 2x4 and plywood into larger assemblies like the CLT and mass timber products you see here. They promise larger buildings, but also bring and more sequestered carbon, but also kind of use a massive amount of material in their construction and ultimately produce largely buildings in which we have straight walls and kind of flat floors and roofs. We see a favorable approach in the work of artist-architect Alan Wexler or Andy Goldsworthy, who recompose and respond to material as it's being used. So on the left, Wexler is actually inserting wedges into the wandering trunk of a tree in order to redirect its line into a straight path. And so those wedges are directly related to the original curvature of that natural material. So the focus of our current work draws on this lineage and this kind of view on timber production. And we're working on a series of prototypes and fabrication processes now to kind of introduce new workflows into this history. Part of this is developing designs that are able to adapt to material inventories. And so this project, Tangential Timber, you'll see a scale model on view in the exhibition in Campbell Hall currently. The project makes use of cross-sections of wood called rounds or cookies in the timber industry, which was sourced together, working together with UVA sawmilling from kind of waste logs on UVA's campus. We deploy here 3D scanning methods to understand the geometry of the material that we're working with, since every piece of material is unique. This builds on the kind of history starting with offices like Frank Gehry's in 1991, deploying a 3D pantograph to digitize a physical model into the computer. And as part of this, we see an inversion or remixing of traditional pipeline of building construction. So instead of a design that's then bid out and sourced and materials are sourced that moves into construction, there's a dialogue now between the kind of input material inventory and the design process. They can respond to each other before fabrication or construction proceeds. So part of this project was developing a custom low data scanning method where we actually make a 3D model of each of these unique cookies using only a single photograph that's traced digitally through Grasshopper and Rhino and is scaled and rotated and kind of track its orientation physically and digitally through these series of markings that are written on the surface of each cookie. Those photographs are then imported and produce a digital model. And the reason we're doing this is that we can then work with and simulate the aggregation of all these unique pieces, without crashing our computers. So it's a lower data workflow using only the information that we need about the form of each piece of material. The pieces are then aggregated according to the form, larger pieces on the bottom, smaller is on top. And joints are water jet with a 5-axis water jet. So you see a kind of notch joinery on the interior of the structure and an overlapping shingle detail on the exterior of the structure because each joint is actually generated directly from the curvature of the input cookie. The surfaces are then cut with the 3-axis CNC in Campbell Hall, and these lines are representing the stress lines running through the material so that the material can be thicker where needed and thinner where less structural forces are present. And they also present a kind of aesthetic of a second wood grain overlaid upon the grain of the actual material. This was a full-scale prototype. Briefly, I'll just talk about a second kind of robotic timber process. A quick prototype done through a workshop at the University of Texas at Austin, deployed kind of traditional industrial robots to work with log geometry. In this case, the digital method was using kind of commercially available photogrammetry apps on your smartphone, which produce amazing images like this. And this is all the parts of the surface that are then stored as a kind of two-dimensional image and then remapped onto a 3D geometry in a software like Rhino. Importantly, you see these lines of this T-shaped mark at the top, the center of the screen, which are important to track how that material is oriented digitally and physically. We then use the shape and geometry of these digital models to generate cut paths and curvatures for the robot to cut that are directly related to that material. And in this case, the tooling was a kind of small traditional woodshop bandsaw bolted onto that robot. And so you get these sweeping geometries coming directly from the material itself. And that was aggregated into a kind of simple column that starts with kind of linear cutting processes on the bottom, referencing traditional sawmilling, and then a branching assembly at the column capital. We're also interested in how material geometry can enhance performance. And so leading into the last set of projects, we've developed a kind of new technology here at the University of Virginia, working with Gavin Garner in engineering. This is a robotic bandsaw sawmill that allows us to cut geometries that are non-planar. We can cut curving and twisting geometries accurately at a large scale. And so this tool brings kind of CNC control, electric motors. It can cut, unlike a traditional sawmill of this scale, it can cut directly from a Rhino model, and we translate that digital model into three-dimensional space and produce new readings of grain, for instance, upending traditional understandings of kind of plane sawn or quarter sawn lumber and what we would expect that grain to look like, because we now have tool paths that are cutting in and out of that natural curvature of the ring structure of the tree.
So we'll show now how some of these technologies and approaches have been deployed in some larger scale demonstrations. The first is Sylvan Scrapple, which was an installation developed for Exhibit Columbus, a biennial exhibition that takes place in Columbus, Indiana. It's a somewhat unique biennial in its commitment to facilitating sustained engagement between the designer and the city in the year of the project design. And it's situated around a compact downtown that's walkable. The city itself has a unique architectural legacy and collection of 80 significant works of architecture, despite its small population. And our project was sited along 5th Street, which is also known as the Avenue of the Architects, a block from the historic Queen Anne style Irwin block, which burned down several months before the exhibition, and then across the street from Elil Saarinen First Christian Church, which was also renovated the same year. And I mention those because those kind of events and renovations informed our material approach to the project. The city itself does face challenges activating its downtown, like many cities post-pandemic, as well as really making the grand scale of mid-century urban design useful for its small population of 50,000. And so our approach was to insert a 110-foot long snaking wood wall into a kind of oversized 2,000 square foot landscape planter, in effect framing a series of elevated seating areas and overlooks. In order to create this wall, we deployed the robotic sawmill for the first time, taking both landscaping waste and demolition material into the process. And we used nested arced cuts to cut members out of curved logs that would produce the arced members for the curving wall. And so here you see some of those initial test cuts of how we could nest arced cuts. The wall itself is made up of a series of arced circles of different radii, as well as straight members that used wood from a reclaimed from a barn. Because the project was temporary, a system was developed to allow for fluctuation in the stacked wood structure over time. So a threaded rod assembly method and integrated spring detail allowed for fluctuations in moisture content of the wood. And then a kind of second material system came into play, which was reclaiming bricks from the building that had burned down just a block away, and relocating them into these kind of custom gabion cages that augmented the existing brick wall. Finally, a 15-foot long table collected construction scraps into a kind of composite surface that could form a center for the installation. So the snaking wall is intended to invite visitors up into the planter and really make the planter a kind of habitable space. It also frames thresholds and provides nooks and overlooks to the surrounding urban spaces. So here's a kind of final image where you can see those three material systems coming together. The second project that we made with the robotic sawmill was a demonstration for a symposium at NJIT last year. And in this project, we're thinking about the kind of nesting of cut members more three-dimensionally than the kind of 2D arc cuts. So for this project, we used ash that had been felled by a disease of the emerald ash borer, and the tracings of the insect on the material actually kind of inform a design approach. So these kind of snaking paths become a logic for these wavy units. To mill the material, a series of wiggling tool paths are cut on the sawmill, producing undulating live edge slabs. And then these slabs are rotated 90 degrees and cut again with the wavy paths, producing boards that have curvature in both plan and section. And so here you see that kind of first set of live edge waving live edge slabs, and then the second series where we get the waves again deployed in the opposite direction. In this illustration, you can see how the resulting cuts allow for actually very efficient use of a straight log to produce a large quantity of wavy units. And they result in uniform units, which are cut on all four sides, and then live edge units, which are cut on three sides, and then of the exterior exposed. So we separated these kind of two types of boards out and created some panels that were uniform and some that expressed the exterior of the log, and then mapped them to different portions of this kind of rectilinear assembly. Seen from above, you see the interior in which everything appears uniformly cut. And then here you see some shots of the top of the assembly where new types of grain patterning informed by the three-dimensional cuts start to emerge. And so one of the exciting things we found in this project is that we start to get a new kind of grain logic that adds to the catalog of rift sawn, quarter sawn, and plain sawn. Finally, you see the live edge units on the bottom and the uniform units above. So I know we want to wrap up rather quickly, so this is the last project, but I think this ties back to the kind of theme of biophilia in exciting ways, where this collaboration with Jenny Rowe was really about thinking about how some of this material work actually affects the brain and cognitive experience. So Sheets and Slabs was a project in which we created two test chambers, and one kind of built on some of the wood techniques we're developing. It's clad in kind of meandering grains of live edge slabs. And the second chamber is more prototypical material assembly with sheetrock. And so the goal with this project was to create these two testing spaces that were exactly the same except for their material finish, and then have our partners in environmental psychology and neuroscience evaluate the effects on occupants. The volumes have openings at the top in order to avoid kind of feelings of claustrophobia, tapering from rectilinear bases into funneled skylights. and then integrated seeding, while obscuring views to outside of the units in order to prevent visual interference into the testing. And here you see some of those headsets that were deployed by the team for the collection of data. So we'll end by sharing, kind of our excitement about both the new potential structurally, but also in terms of how we can deal with the expressive qualities of material, and look forward to continuing this dialogue.